All right, so I want to finish off the discussion on inverses.
Could use that.
So as Matthias realized the other day, the point of the inverse matrix is that it is doing the inverse linear transformation. And that might suggest inverse function of the corresponding linear map. But you might wonder, if I had a non-square matrix, could it have an inverse?
I suppose. If it was the opposite dimensions.
So could there be an inverse for a non-square matrix? So what would that mean? So you'd be, if you had a mapping from, if you had an m by n matrix, you'd be talking about a linear map that went like that. And what would it mean to have an inverse? Well, it should have to go back, right? Like inverse function should go backwards. So the question is, can that happen? If we had a t going here, could there be an s so that if m doesn't equal n, could we have a transformation? So we go from Rm to Rn with, so you would want to say if I start here and go back and then do t, I should come back where I started. And similarly, if I start with any x here and do t of it and then s back, I get back to x. Do you guys know or remember something about just when, if you just have mapping between two sets, what does it mean to say that these kinds of equations can hold? Does anybody know this?
Onto?
Yeah, one-to-one and onto, right? You actually have to have the function t be hitting everything in Rm and no two things in Rn go to the same place. Do you think that can happen?
Sure.
Yeah.
With m and n different?
No.
So we don't have a means to prove that yet, but so later on in chapter 4, we'll return to this. So we want some way of measuring the size of how much gets hit by the function and whether the two things end up going to the same place or not. So those are going to be important concepts. All right. So couple of things. Here's a general formula. I did an example for you the other day. That if you multiply a 2 by 2 matrix A, B, C, D by the matrix D minus B minus C, A, what do you get? Neither. Not yet.
You get the
So you get AD minus BC. You get minus AB plus BA. CD minus CD. Minus BC plus AD. So what can we conclude? And I'll tell you that it works the other way too. If you turn them around, same in the other order. So what conclusion can you now draw?
It's a scale of the identity matrix.
And if the scalar isn't, can you rig it so that the answer will be the identity?
Yeah.
Multiply by 1 over. What are you assuming when you tell me to do that?
It's not 0.
It's not 0. So, provided this mystical number, quiet all of you who know what it is, isn't 0,
You used it in the chapter.
provided AB minus BC isn't 0, we see that the matrix 1 over that scalar times B minus CA will be the inverse. So this is some sort of interesting quantity which we're going to understand quite well by the end of the hour. So I want to do two things as applications of inverses. First thing I want to comment is if A and B are both invertible n by n matrices, what do you think is true about their product? Also invertible? How can I prove such a thing?
You put A and B inverse in terms of A and B and inverses.
So you're saying, give me, if knowing that A and B are invertible, you have their inverses, and you're going to give me a formula for the inverse of AB?
Yeah.
So in particular, Matthias, what's the formula?
I don't remember exactly.
Is it the inverse and inverse just like
That's what B inverse transpose.
So this is like what we did with transposes yesterday, except I'm going to actually call this the shoe-sock theorem. Remember that matrices are representing linear maps, linear transformations. Okay, we can debate linearity, but think of functions where you first put on socks, and the second function puts on shoes. How do you undo that? What's the inverse function of that composition of functions?
the shoes.
So that's what this is doing. This is saying, put on the socks, put on the shoes. To undo it, you first remove the shoes, and then you remove the socks. You'll never forget this, right?
Except for when I get socks.
So the proof is, you forget all the time?
Yeah.
That's why you don't wear socks, because it makes it too hard for you. So the proof is, let's just check that this satisfies the definition of inverse. So if I take AB, and I multiply by this putative, alleged inverse, if it works on both sides, then it's the inverse by definition. Well, what can I do with this?
So B inverse.
I can regroup by associativity. This is the identity. And multiplying anybody by the identity is just the same as not having the identity there at all. And so I'm done. And you can see that to make things cancel, you need to reverse the order here. Right? It's the same thing as with the socks and shoes. And similarly, on the other side, right? Same idea, but now you're using A in the middle. Okay. N. So this will be useful at numerous times through the course. Any questions on that? So I want to give you an application of the invertibility for 2 by 2 matrices, and then perceived. So here's an application to a question from section 1.1 or 1.3 or something. It did come up, I don't remember when it came up. Suppose I give you two vectors in R2. So suppose U and V are two vectors in R2 that are non-parallel. Somebody asked, or somebody said, I've forgotten who it was, that I could get any vector in R2 as a linear combination of those two vectors. Namely, the fancy language,
U and V span.
they span all of R2. So that's obvious if U and V are what vectors? Standard basis vectors. But if I take two weirdo vectors, maybe it's not obvious. So if I took U and V like that, maybe it's not so obvious that I can get every vector as a linear combination of them. Well, how do I want to prove this? I want to take an arbitrary vector x and ask what?
What is it in terms
Can it be written as a linear combination? So given an arbitrary x, are there scalars C1 and C2, Alex, so that what's true?
So that C1U plus C2V equals that?
Excellent. Everybody got that? So can you write this as a matrix equation for me?
C1U over C2V? No.
So I have a vector x, and I'm asking what matrix operation says take linear combination with certain scalars?
Dot. Multiplication.
And then A
Multiplication.
minus something.
You multiply
So-
two.
UV is one matrix.
UV as the what?
A matrix. No determinants.
No.
Columns.
Columns.
Oh, yeah, oh, okay,
And then what happens with the C's?
yeah.
There are the entries of my vector, right? I'm asking, is there a vector of C's so that this matrix times C, I'll write it this way, equals X.
Couldn't you just say that U and V are composed of aspects of the standard basis?
Sure, but
and
then what?
And then just
And you just
show it as
Another-
that and show that.
Well, but I mean, ultimately, you better use non-parallel if you're gonna make this assertion. So somewhere I better see something about non-parallel.
And then you can multiply by the inverse,
Yeah.
How do I know there is an inverse?
because they're non-parallel, so AD minus BC is not equal to 0.
Okay, so you're seeing that very quickly. So if you had the vector u, which I thought of temporarily as AB, and you had the vector, actually not AB, AC. And you had the vector v, which you thought of temporarily as the vector BD. What Nick is saying is that non-parallel is saying that that quantity isn't 0. So note that u and v are parallel, if and only if
A equals this,
AD minus BC is 0. Why in the world is that true?
because A and C are going to be scalar multiples of B and D, and vice versa.
So AC equal a scalar, I better not use the same letters, T times BD means,
So then,
so A is what?
TD,
And C is TD. And so, what's AD minus BC?
TBD
2B
minus TDB, which is 0.
Easy for you to say.
Can you just rearrange the equation to be like the slopes of both of the lines?
Yeah, the reason I didn't do it that way is I didn't want to worry about what if I'm dividing by 0.
Okay.
But that's the way you should think about it. So
Okay.
Mallory's saying, think about the slope of the vectors and think about similar triangles. But I didn't want to think about dividing by 0.
How do we get that AC is a scalable with BD?
Well, saying they're parallel,
Oh, okay. Yeah,
Right.
okay, yeah.
for some scalars. And so this is T times
BD minus BD.
A BD minus DB. So that's 0. So non-parallel means this matrix is invertible. And this means that you can now use algebra to solve the equation. So because A is invertible, I can take this equation and solve by multiplying by A inverse. And you will have web work to do such things. Cal, do you have a question?
Yeah.
Mhm.
So the example that we did the other day of a non-invertible 2x2 matrix, like 1, 0, 2, 0,
Mm-hmm.
those, no, those are those parallel?
Yeah, remember the 0 vector is parallel to everybody.
But the vector 1, 0, and 2, 0, oh, because those are just along the x-axis, right?
Yeah, right.
Okay.
That's right. That's right.
Okay, so it does hold them, yeah.
Yeah.
Gotcha.
So if I assume that I have a solution and try to find it, I would multiply on the left by A inverse on both sides of the equation. I would then do what over here?
Regroup.
Regroup and use,
Yeah, then
so this is A inverse A, C equals A inverse X. This is the identity, so C is A inverse X. We're not done, folks, because I assumed that there was a solution when I did that. So what have I got to do to be logically correct? Louder? Well, I mean, here is the candidate for the solution. I have to check that it really works. Right? Check, C truly is a solution. It's a candidate. This is like stuff you did in high school where you got extraneous solutions. You had to make sure that you got rid of the extraneous ones and that the honest ones really were solutions. So I have to take, what is AC?
A times A inverse.
Right? It's A times A inverse X, which is X. Done. We're fine. Now,
Did you just multiply both sides by A?
well, I wanted to see
You went back
that
to-
AC really was X, so I went back to the original equation, and I said, what is AC if this is C? So I did multiply by A on the left, yes.
Okay, okay.
So Matthias, you have a,
It just looks like the exact same thing you did to get to AC, like, it literally.
well, I wanted to make a point about that. It isn't. Notice I'm using both parts of the definition of A inverse. Here, I used one order of multiplication, and here, I used the other order of multiplication. I'm using it on both sides. So it really is essential that you have both criteria when you say An inverse is a matrix which when multiplied by A gives the identity. You have to have it on both sides. And you see why, just to solve the equation and then check your solution, we're using both arrangements. Students are always surprised by that. Don't be surprised. It's important. Okay? All right, so as I said, you will have some web work doing this. Don't come running to me saying I don't know how to do this problem when I've just shown you how to do it. You'll have numbers in it, so I haven't done you an example with numbers, but you're going to have a couple of questions on it like this.
So we proved that the solution is A inverse times X.
Right, so given any x, how do I find the scalars that tell me what linear combination to take? I take the inverse of this matrix times x, and those coefficients
Right.
of the answer tell me the scalars.
Okay.
Sort of cool.
So, that's around that or
Any other questions? All right. So I want to now proceed into section 5 and talk about today and on Friday and a bit more on Monday, what is the meaning of this quantity AD minus BC, comma, anyhow. It looks like a dot product, doesn't it? So if I have the vector A, C, and the vector BD, I wish I had arranged them differently now. Is there anything I can do with them that will give me this quantity as a dot product?
Flip D and B and make B negative.
Well, I don't want to make B negative because I want A times D.
If you rotate one of the vectors, then you can switch the order of them and then dot them.
AC dot, I want AD, so this better be a D, and minus BC, this better be a minus B.
So you've rotated it.
Or I could rotate, I could do it the other, could put the minus sign on the other one.
Sure.
Right? I could instead do BD here and say we want minus C there and A there. So what's the meaning? I'm going to go with this one just because you'll see why. But what's the meaning of the vector negative CA?
You've rotated it 90 degrees counterclockwise.
You rotate this vector 90 degrees counterclockwise, and you get the vector negative CA. Remember that we did the rotation matrix for a rotating triangle theta? We did the 90-degree one first. So what are we doing when we do this dot product? We're dotting this vector with this vector. What does this mean geometrically? So if this is the vector u, and this is the vector v, we're saying this quantity is what I get when I rotate u by pi over 2. I'm going to use rho for that temporarily. And dot it with v. So here by rho I mean rotate pi over 2 counterclockwise. What's the meaning of dot product? I've forgotten.
It's the area.
No, no, no. What's the meaning of dot product?
It's the length of each vector times the cosine between.
Length of this vector, no, length of this vector, but they're the same, right?
Right.
Yeah.
So this is going to be, let me try to squeeze this in down here. This is going to be the length of rho of u,
Which is the same as.
which is the same as the length of u, times the length of v, times the cosine of what angle in this picture?
Rho of u
Nine
minus v.
It's going to be this angle, right? I'll call it phi. What's cosine phi the same as?
Cosine of 90 minus theta, which is sine of theta.
So if I put theta in there, I would have what quantity?
Sine theta.
I'd have sine of theta. So rho of u dotted with v is the length of u times the length of v times the cosine of phi, which we said was the length of u, length of v, sine of theta. Because theta and phi are complementary angles there. Anybody remember a geometric interpretation of this?
The area of the
Where's magnitude v sine theta in this picture?
Is that twice?
is the height of the,
It's the like component.
it's the projection into.
No, it's not the projection. This is the projection.
All right, the
That's
component.
cosine. Where's sine theta? So this is magnitude v sine theta. So what am I doing? Length of this guy times this.
It's the area of the square.
Area of parallelogram. Right? The area of the parallelogram spanned by u and v is exactly this quantity. Cal, you look unhappy.
No, I just had a conceptual question. So, over there, if AD minus BC equals 0, then AD and BC are orthogonal, right? Or the dot product of AD and BC?
No.
They're parallel.
No, they're parallel.
Because you rotate
Because
the
when you
one,
rotate one of them, then they're orthogonal.
yeah, then you take the dot product and then it's zero.
Oh, so if you rotate 90 degrees and it used to be parallel, now it's orthogonal,
Right.
it's 0. Okay, that's where I was confused.
Got it?
Yeah.
So this is I'm going to put area in quote marks for a minute. I'm not sure if Dan's in charge of these quote marks or not. Area of the parallelogram spanned by u and v. Why did I put the word in Dan quote marks?
It's actually.
Hmm? Well, we're not there yet, but
It's.
this quantity could be
Negative.
negative. In fact, if the picture were u going like this and v going like this, with theta going from u to v that way, you would get a negative number here because you'd have sine of a negative angle. So, in what sense is it area?
Absolute value.
The absolute value of it is the area, but do you remember a concept like this came up when we were first doing projection, and we talked about how if you projected and the picture looked like this, you got a signed length, you got a negative length when you did the dot product? This is analogous to that. So I'm going to actually remove the quote marks, take Dan off the hook, and call this signed area. And the convention on the sign is that when the picture looks like this, the signed area is positive, and when the picture looks like this, the signed area is negative. So, do you have a way of conceptualizing that?
Because counterclockwise.
Going from u to v, if you go counterclockwise,
Positive.
Just like.
as long as you go counterclockwise less than pi, right? You could go around from here to there, and that wouldn't count as going counterclockwise. So the convention here is that theta has to be less than pi in absolute value. You can't wrap all the way around. You guys get what I'm talking about? Yeah. Right? You take you draw yourself an imaginary line in the negative direction, and you have to stay either here or here when you put v in. So you either put v here, or you put v down here, and you measure the angle correspondingly. So here the sign will be positive, here the sign will be negative. Okay. All right. Well, so this creature that we've just talked about associates to every 2x2 matrix a number. And that number is important unto itself. So if I had these a 2x2 matrix with its column vectors, then I would call the determinant of A, which is written det A for short. And it's also written by putting vertical bars instead of brackets on the matrix. So for example, if I gave you 4, 7, negative 3, 1, the determinant would be
4 plus 21.
So be very careful with negatives and negatives when you're doing this stuff for the next few weeks. So if I think of this thing algebraically or geometrically, I can think about properties of this as a function of a pair of vectors. So I can consider a function of, say, two vectors x and y, which I'll call script d for today, and Friday as well, where x and y here are in R2, where the formula for this is what we've just been doing. So I'm not putting x and y the way we've been writing vectors vertically. I'm actually purposely writing it in your classical function notation, because I'm thinking of this as sticking them in as columns of a matrix, and so I'm lining them up for you. Right? X and then y, and this is going to be, if you had coordinates for your vectors, it's the same formula we've been using. This product minus this product. So let's think about what properties this has. So I'm back to our recurring theme of using algebra to do geometry and geometry to do algebra. Let's see. What happens if I switch x and y?
Negative.
So if I switch these two columns, the sign changes. Does that make sense from this perspective? If you switch u and v,
Just changes the angle to
then the angle becomes the negative,
Sure.
right? Because you're now going from here to here instead of from here to here. Okay, so that one is clear from the algebra, and it's also clear from the signed in the definition of signed area. What about putting a scalar in on one of the vectors?
Sure, it pops out.
Equals C, yeah.
So if you put c times the x's, what would it do to this formula?
C times the
Just by the distributive property, it pulls out. And similarly, that would be d of x cy, right? You put it on the y vector as well. Do you see that geometrically?
Because it would,
What are you doing to this parallelogram if you replace one vector by c times it?
making it longer or shorter. And
Right?
so
You're
then,
stretching it or you're flipping it, either way, you're
by multiplying,
adjusting the signed area by that factor.
you're still getting.
All right, this one's more interesting. What is d of x, comma, y plus z?
Because y plus z. Does it, does it distribute?
I mean, I don't know, does it?
You don't do that.
If you look at this formula,
I'm thinking it distributes out. Because it would kind of shatter everything we've
So
learned.
it's like, yeah.
so I'll do the check over here, but in fact, it does give you a sum of two determinants, one xy, one xe. And what's the algebra for that? The algebra is, you put y plus z's in here, and then you just use the distributive property. Does everybody see it? You want me to write it out? No? It's in the book if you want to read it in the book. Okay, so for all you skeptics back there, how do you see this algebraically? I mean, geometrically?
It's a linear transformation.
It's like the sum of two areas of parallelograms. It's two parallelograms and you add the areas.
And since I did not think about this ahead of time, I'm no doubt going to mess this up. But you should be able to see it pictorially if you draw the picture carefully. If. So if I do x, and then I have y here, and I have z here, then I should be able to see that if I take the parallelogram corresponding to y, I'm going to change my z to make the picture less confusing. I'm going to make z longer here. So now the parallelogram corresponding to z looks like that. And where's x plus z? I would use purple, but you guys can't see purple.
Like x plus c or y plus c?
I'm sorry, y plus z.
It's just make a little parallelogram there.
So I now have a green parallelogram using y plus z. Do you see? It's not totally obvious.
They should be.
Y is the area of the green,
It
the
should be
sum
this-
of the red and the blue.
This one right there.
You can add the little triangle that's outside on the left back in
Yeah,
on the right.
and then just
you can
transpose
move the
that
blue
guy.
one up.
So you're saying this guy?
Yeah. Then move it to the other edge.
So where does it go?
Can
It
fit
goes
in
here,
right there, yes.
and then,
You have to pull
The blue one just transposes.
the little
up.
extra part of the blue needs to go back
Well, you
underneath.
can tilt it.
In between the green and
You
the
have
blue.
to tilt
between.
Z a little bit,
Well, that's, yes.
but it'll keep the same height.
You put it there,
so this thing should be moving where?
right there. Go left. What?
Ah,
It's in between the y and y plus z.
Yeah.
To extend
so
the,
I've got the red area already. I don't want to be inside the red area.
Correct.
oh,
it has
you
to go up here.
shift
That
it all the way up, yeah.
parallelogram
Okay.
has
All right.
base
What's the little
X.
blue part?
I was gonna get the whole area together and then.
So I shift the blue guy, so it's, instead of being here, it's here. And then I have that area. Well, this wasn't inside the green, but this piece corresponds to that piece.
That's it.
Matthias is now blind. So you can actually see it purely geometrically, but the algebra is obvious. All right. Here's a question for you. What happens if I take d of x, comma, y plus scalar times x.
Scalar times x.
Yes, scalar times x. So I'll draw you a picture of this one. X, y, and then I take y plus a scalar multiple of x. What does that do geometrically?
Makes it
If I add a scalar multiple of x to y, what am I doing?
Extends.
I'm,
Something in between.
You're changing the angle between the sum and.
I'm moving y, the head of the arrow for y, parallel to x. So I would end up over here. Agreed? Y is the area of the blue parallelogram, the same as the area of the yellow.
Because if you do the.
They have the
algebra
same
operations,
base and the same height as the
They
shear.
have the same base and the same height. Or geometrically, this triangle just moved over there.
You can also see it algebra.
What's this? So
It's like tilt, like,
this is called,
a shear.
It's called shear.
although we might want Den to be shorn for that remark. This is called a shear. If you've ever taken geology, you learn that layers of the earth slide along one another. That's this procedure where you move this guy parallel to x. It does not change area because the base and the height stay the same. Can you see this algebraically? Well, it's dxy plus dx cx. Oh,
Since
That'll
x and
understand.
cx are parallel, so it's.
That'll be,
well, but we're doing it just algebraically, no fair cheating.
Oh.
it's equal to 0.
Why?
Wow.
No, y is over on the other part.
Because it's d
Think
dx.
first.
It's c dx x.
Pull the c out.
Determinant.
Yeah, the determinant of
since
x.
it's the same value
Oh, that
of
makes
parallel.
Now you're using geometry.
No.
All you're allowed is the three rules.
Okay, you have
The
x1
components-
times x2 minus
x1 times x2.
All right.
Yeah.
Can you do it from the properties and not just from the formula? But you're absolutely right, Mallory. What property on that list tells you that if you put the same,
One, yeah.
good Matthew, why?
Because if you have d of x
Yeah.
comma x, it's equal to negative and d of x comma x.
There you go.
Yeah, you know, look at you and.
Plus that.
What number,
Zero.
what real number is equal to its negative?
0.
Any others?
No.
No.
Number times.
You already met this concept looking for skew symmetric matrices when you were doing web work, by the way. Okay, so dxx is 0 for 93 different reasons. So by algebra, you see that shearing in fact doesn't change the determinant. Okay, so you understand two-dimensional signed area. And you see that the geometric interpretation has the same algebraic properties as the algebraic definition gives you. So now what can you do in 3 dimensions? Well, what's the natural generalization of what we've been doing to 3 dimensions?
You can use a three-dimensional parallelism.
So you want 3 vectors,
Yeah.
or I could call them x, y, and z, or u, v, and w, it doesn't much matter.
Parallelism.
And you could look at the parallelepiped. 2 points if you spell it correctly. So you take x, u, v, they span a parallelogram in space, and then along comes a 3rd vector w, and you then have a 3-dimensional box.
Sheared cube.
It's like a sheared, well, it's not a cube, but a parallelogram, sheared rectangular box, right?
It's like
So
if
you might similarly want to talk about the signed volume of that box. Or you might similarly want to talk about a function that eats 3 vectors. So this is notation I haven't taught you yet. This means you're going to feed in 3 things to D, each of whom lives in R3. So this is called Cartesian product. We won't worry about it too much till later in the course. So this is going to say dx, y, z, I keep not knowing what letters I'm using, is the signed volume of the parallelepiped spanned by x, y, and z. So there's a geometric notion, and I will finish for you by giving you the algebraic definition, and then we're going to spend Friday using this stuff. So here's the definition. Most of you have seen some version of this, except you're used to rows rather than columns.
Yeah.
So here's x, here's y, here's z. And the way you define this determinant, and again, on Friday I'll talk all about what this all means and how to use it for stuff, is you pick on the first column and you say, okay, you have to sit out at recess, you don't get to go play with the others. And you take the first thing in x, and you multiply him by the determinant you get of the remaining 2 rows of y and z. You take the second element of x, for some bizarre reason, which you will understand 6,000% in the spring, you put a minus sign. And then you remove the second row of the y's and z's, and you put the first and the third. Take that little determinant, which you already know how to do. And then lastly, you put the last x times the determinant of the first and second rows of y and z. So that's a formula. What in the world does it mean? How many of you have seen this before? Not everybody, okay.
If you see
It's
like a
mentioned
version
by
of it,
minors, right?
Now there is a shortcut for this, which I will show you on Friday, and that is that you can, for example, you can take your determinant and you can write down the first 2 columns yet again. We'll see this in the book as well. And you can then do this product, and this product, and add those up, and subtract this product, and this product. If you write out the algebra here, you get 6 terms, and that's exactly what you're doing. Okay, so what does this all mean, and what's it good for? Come back Friday. Get to work on web work.